हो गया सब्जी। Okay, those who have just joined, please add your SAP IDs in the chat section. Okay, those who have not added their SAP IDs in the chat section, please add so that I'll have a record of your attendance. Okay, so I think we can start now. Is everyone ready?
Yes, sir.
Okay, we'll start. So in the previous class, we had seen the basics of our gas turbine power plants. We had classified the gas turbine power plants mainly on the basis of the type of cycle that they employ. Uh, we had, of course, had a small brief about the gas turbine power plants that are there in India. We had concentrated more on the ones that are there in Maharashtra and Gujarat. We had seen the layout of the gas turbine power plant. The basic components would include the compressor, the combustion chamber, the gas turbine, and if it is a closed cycle power plant, then there will be an additional heat exchanger which is going to reduce the temperature of the working fluid. So this is the layout of the plant wherein you have the oil storage. If it is a plant that is operating on gas, then there's going to be a pressurized gas pipeline which directly feeds into the combustion chamber. So we had discussed in detail about the open and closed cycle power plants. This is how the layout looks like, the schematic diagram of a closed cycle gas turbine power plant. So we have discussed the various advantages and disadvantages of closed cycle gas turbine power plant. Then we have discussed the open cycle power plant wherein you require an additional air filter to filter the air that enters the compressor so that the dust particles don't enter the compressor. We had also discussed the advantages and disadvantages of open cycle gas turbine power plant, and we had come to a conclusion that the open cycle gas turbine power plant is more uh, proficiently used because it includes direct heating, and of course it occupies lesser space. We had also discussed about the PV and TS diagrams for the simple gas turbine power plant. And we had this derived the expression for the efficiency of your simple gas turbine power plant, and it is given by 1 minus 1 upon Rp raised to gamma minus 1 by gamma, where Rp is the pressure ratio. So today we will be more concentrating on the methods to improve the efficiency of a simple Brayton cycle or a simple gas turbine power plant. Basically, these are the three methods that we can employ to improve the efficiency of your simple gas turbine power plant. The first one is intercooling. Okay, so intercooling, you all have studied what intercooling is. Basically, if we are trying to compress an air to a very high pressure issue, okay, of more than 6, then what happens is that the temperature rise during the compression process is too large, and that causes the expansion of the gas as it is getting compressed. So it works against the compression process. So it is always beneficial to compress the gas in two stages or more than two stages depending on the pressure issues. So if you are operating of pressure ratios of more than 6, then it is advantageous if you have a two-stage compression process. So same thing applies over here. You have your compression carried out in two or more stages. Uh, if the pressure ratio is above 4, uh, here a water cooled heat exchanger is used between two stages. This obviously is going to reduce the work of compression because you cool the compressed air to its initial temperature. Okay, that is the ideal case wherein you cool the compressed air after the first stage to the initial temperature, that is the temperature of air before compression of air in the first stage. So this obviously reduces the work of compression. So this is how the schematic of your two-stage compression employing intercooler is. Here, uh, here we can see that your air enters the first stage of compression from here. Okay, and it enters the compressor. It is getting compressed. Uh, if you are just considering the ideal case over here, so it is getting compressed isentropically. Okay, from 1 to C over here. Uh, and the compressed air then enters the intercooler. Okay, here it is again cooled back to its initial temperature. Here you can see 1 is fairly equal to T. Now that is in ideal case we assume that one is T1 is equal to TT. Okay, but in actual that never happens. So we are just discussing the ideal case right now. So after the intercooler, the air is again sent to the second stage compressor, okay, where it is compressed from D to 2. Okay. So for perfect intercooling, your pressure ratio, sorry, your intermediate pressure, that is P2. P2 must be under root of P1 into P3. You are very well versed with this expression. Okay. P2 is equal to under root of P1 into P3. So next we'll go to reheating. Now what is reheating? Reheating basically means that here you can see you are expanding the turbine in two stages. So if we are doing that, we can reheat this products of combustion that are leaving the first stage turbine. So we can reheat again by external means, so that you will tend to increase the efficiency of the cycle. Okay. So in reheating, the combustion gases are not expanded in only one turbine, they are expanded in two turbines. And the exhaust of high pressure turbine is reheated in an external reheater and again expanded in a low pressure turbine. So here your power output is obviously increased, but at the cost of using additional fuel, because we require an external reheater over here, right? We require an external reheater over here. So you will require additional amount of fuel to add more heat to this reheater, and of course because of this increase in the fuel consumption, your net efficiency will go down slightly, as it is shown in this graph, but your power output is going to increase. So you're increasing the power output at the cost of increasing the fuel consumption. Next is regeneration. Okay, here what happens is the heat from the gases that leave the turbine can be used to preheat the compressed air that is just coming out of the compressor. So this naturally increases the thermal efficiency of your plant. Okay, so over here in regeneration, the heat from the exhaust gases is transferred to the compressed air, okay, before it enters the combustion chamber. Now this leads to saving in fuel. Okay, because you in previous case where in case of reheating you were using additional amount of fuel to reheat your products of combustion that leave the first stage turbine, but over here you there is no need of additional fuel because you are utilizing the excess energy that is there, uh, that is coming out of the turbine to preheat the compressed air. Okay. So this leads in reduction in waste heat that generally goes unutilized. Okay, so here you get increased power generation as well as thermal efficiency. Okay, so this graph clearly depicts the comparison between the two cycles, that is the simple gas turbine cycle and a regenerative gas turbine cycle. Okay, so what happens is most of the case in your open cycle gas turbines, this uh, products of combustion that leave the turbine, that is this one, they are generally left to the atmosphere for a free expansion. So they have a lot of energy. Okay, their energy, the temperature is in most of the cases above 400 degrees Celsius. So this is waste of additional thermal energy which can be utilized. So this can simply be utilized here in a regenerator. So this is going to increase your thermal efficiency of your plant. Okay, I hope these three methods are clear to all.
Yes, sir.
Okay, so next up is your gas turbine combined cycle power plant. Okay, now as I was mentioning previously, your this uh, products of combustion that leave the turbine are at more than 400 degrees Celsius. So they still have a lot of heat energy uh, to power additional steam turbine. Okay, now exactly this is the exact thing that happens over here in a GTCC power plant, that is gas turbine combined cycle power plant. The exhaust gases uh, that the exhaust gases that leave the turbine over here, they still have a lot of energy. As I mentioned, they are most of the cases above 400 degrees Celsius. So they are allowed to pass through a heat recovery steam generator. Okay, here the heat energy is transferred to water to convert it into steam, and then that steam is again sent to a simple steam turbine, which is coupled to a steam generator. So you have got electricity generation from your gas turbine as well as electricity generation from your steam turbine. So this is the most common configuration that is being used currently in most of the modern gas turbine power plants, wherein they have a combined cycle. Okay, that is the gas turbine cycle as well as the steam turbine cycle. So they have both the cycles operating just because their gases at the exit of the turbine have a fairly large amount of heat energy. Okay, is this clear?
Yes, sir.
Okay, so now what we are going to do is we will solve a simple numerical. Okay, we'll solve a numerical. I want all of y'all to uh, get ready with your notebooks and your calculators. Okay, you can note down this question. Okay, please let me know when you finish noting down the question so that we can proceed. Have you finished noting down the question?
Yes, sir. Done.
Yes, sir. Done.
Okay.
Yes, sir.
Okay. So this is a fairly simple type of numerical, uh, wherein your basic temperatures are given, the pressures are given, the compressor and turbine efficiencies are given, and we need to find these all things. So first we'll start making the TS diagram. Okay, you should always begin with drawing the TS diagram first. Okay, so that we'll have a fair idea about the processes that are taking place. Here in this case, T1 and T3 are given, the pressure ratio is given, so we can straight away find the temperature after the isentropic compression, that is T2A over here. So you can start solving simultaneously. So you should get T2A as 443.9 or 444 Kelvin.
The T1 is 10 degree Celsius or 20 degree Celsius? In question, it is mentioned 10 degree Celsius.
Okay, okay, you can take it as 20 then. You can take it as 20.
Okay, sir.
So generally these numericals on gas turbines are fairly simple. Even if they will appear in the exam, you should not skip them. They are fairly easy to score marks. So is everyone getting T2A as 444 Kelvin?
Yes, sir.
Okay. So next we can find the temperature after the expansion, that is your after isentropic expansion, that is T4A, because T3 is already given in the question. So it is simple calculation. You can find the temperature after isentropic expansion. You should be getting around 741 Kelvin.
Yes, sir.
Okay. So next we can find the actual temperatures after the compression process and the expansion process, that is T2 and T4. So using the formula of your compressor efficiency and turbine efficiency, we can find the actual temperatures after the compression and expansion processes. So why is the strength so less today? I mean, people are still sleeping or what? Or they are not interested? Yes, Neil?
Sir, sir, I don't know, sir.
Okay. What about A division?
Shikhar.
नहीं सर.
पता नहीं, या सोए हैं सब अभी तक.
So T2 554 आ रहा
T2 554 आ रहा है.
नहीं सर.
है.
नहीं 481 आ रहा है
481 आ रहा है.
481.7
आ रहा है.
Okay, just check हरंगड़. तुम्हारा कुछ कैलकुलेशन एरर हुआ रहेगा. Okay, anyone found T4?
Sir, I'm just. हाँ sir. T4 is going to be 741.27 sir. सर वो 4A है सर, मैं 4 बता रहा हूँ.
Okay, okay.
Sir, I am getting 817.62.
817.6. Okay, that's right. Is everyone getting T4 as 817 Kelvin?
yes sir it's 17.6
Okay. So next is we can find the work of actual compression. which is equal to Cp into the temperature difference, that is Cp into T2 minus T1. So you should be getting around 189.5 kilojoule per kg.
So I have a small doubt, sir.
Yes.
So in the TS diagram, we
Yeah.
are having two like we are having two cycles, right? One is hypothetical and one is actual.
Huh.
So can you explain from the hypothetical cycle, how do we make the actual cycle? If you can explain that.
You mean to say this actual process?
Yes, sir. How do we make the actual cycle from the hypothetical cycle?
No, actual means your hypothetical cycle means your processes are isentropic. Okay.
Isoentropic process is, you mean to say, ideal case.
Yeah, ideal case the processes are isentropic. 1 to 2A and 3 to 4A.
Okay.
And 1 to 2 is an
Okay.
actual process. So generally, because of your losses in the compressor and turbine, and because of irreversibilities, your temperature after the compression will be higher than as compared to the temperature of after compression in ideal case. So T2 will always
Okay.
be higher than T2A. That is what we have been studying since thermodynamics, right?
Okay. Okay. Okay, sir. So the two, so in 2 and 4A, A could
Ah.
have been easily replaced by dash or some other sign like that, right?
See, this is generally the nomenclature that we have been following is 2 dash for ideal and 2 for actual.
Okay.
So because I
Okay.
was
Okay.
not having my
Yes,
own
sir.
notes with me, I had to take this numerical from some book.
Okay.
So that hence the confusion.
Okay.
मेरा सब notes उधर ही रह गया है,
Okay, sir.
कॉलेज में ही
Thank
है
you.
मेरा सब notes. ठीक है. So is everyone getting work of compression as 189.5 kilojoule per kg?
Yes, sir.
Okay. So we'll proceed now. Okay. So now we can find the work of expansion as well, which is equal to Cp T3 minus T4. You should get around 307 kilojoule per kg. And then the net work is work of turbine minus work of compression, which you should get around 117 kilojoule per kg. Is everyone getting net work as 117 kilojoule per kg?
Yes, sir.
Okay. So next we have to find out is the efficiency of the ideal cycle. So it is, since the ideal cycle the efficiency only depends on the pressure ratio. So we can use this formula 1 minus 1 upon Rp raised to gamma minus 1 by gamma. And you should get the efficiency as 34%. Is everyone getting thermal efficiency of ideal cycle as 34%? Shall we proceed?
Yes, sir.
Okay. So next you have to find is the thermal efficiency of actual cycles. So here you will have to use the actual temperatures that you have found out. The thermal efficiency in simple terms is heat supplied minus heat rejected upon the heat supplied. That is the net work done upon heat supplied. So here you will be using the actual temperatures that you have found out. Okay, so simplifying, you should be getting this formula that I've circled. Just need to substitute the actual temperature values to find the thermal efficiency of actual cycle.
Sir,
Yeah.
it's possible for you to explain how the last part works, the airflow rate formula?
Okay. Okay.
Yes.
So airflow rate, this essentially is the ratio of the total power that the plant generates, okay, divided by the net work, that is kilojoule per kg. Now this is analogous to your, if you remember in refrigeration effect where we used to refrigeration RAC, where we used to find the m dot, that is the mass flow rate in the refrigerant system, that was equal to the total refrigeration capacity. Okay, if you remember
Yes.
total refrigeration capacity upon refrigeration effect, that was H1 minus H4. Okay, so here
Yes.
here you are substituting what the refrigeration effect was in kilowatts. Okay, that is kilojoule per second, and this
Yes.
was what was this in kilojoule per kg,
Yes.
right? So the net the resultant unit was kilogram per second.
Yes.
Okay.
Yes, sir.
So it is similar to this only. Here your 25 megawatts are generated. 25 megawatt hour is generated. So 25,000 into 3600 divided by your net work output that you have found out, 117.4 kilojoule per kg. So resultant unit that you get is kg per second. Okay.
Okay, so we had megawatt hour, the unit was there. Okay.
Yeah. Okay. So only I think there's less than 1 minute remaining.